So fun with perlite, right? So we talked about growth of ferrite, single-phase ferrite, in terms of electromorphic and idiomorphic ferrite as diffusive transformations, and Widmanstätten ferrite as a displacive transformation. And now we're moving into the ferrite plus cementite part of the phase diagram, right? And just a reminder, cementite is Fe3C, and it's thermodynamically unstable. This wants to decompose into iron and graphite, but that takes a very, very long time. So it's highly metastable below the eutectoid temperature, right? Okay. And so if we come down from the eutectoid point, right, perlite is the eutectoid structure. So if we're at the composition, the eutectoid composition, and we completely solutionize into the austenite regime and drop down to below the eutectoid temperature, we will get a microstructure that's completely composed of perlite, and it will be 88% ferrite and 12% cementite, right? Just coming off the lever rule, right? So it has a relatively small heat of transformation involved, right? So it's roughly about 1/4 the heat of fusion for pure iron. Right? The thing that's important to remember is perlite's a composite. It's not really a phase in the thermodynamic sense of the word. We call it a phase, but really it's a mixture of two different phases, cementite and ferrite. Right? So here we have these plates of cementite in a matrix of ferrite. And I love this picture because really we have to remember that it's a three-dimensional structure, right? It's really these plates, right? It starts from a point, nucleates out in a sphere in these layers. So it's like layers on an onion. But of course, they can branch and do all kinds of stuff. So it's really more like the leaves of a cabbage, right? When you look at it in a 2D cross-section, it's hard to imagine what the structure actually looks like. But these are 3D plates that are bent around each other in this complex, largely equiaxis spherical arrangement, right? I guarantee you, if you give most people if someone had never seen a cabbage, right? And you just gave them this and you asked them what the shape in 3D was, our brain doesn't work very well at trying to put the 3D picture together from 2D information. Right. But so remember, when you look at this, these are not plates that grow perfectly normal in and out of the surface. They're curved in 3D. And they make this cool sort of cabbage stuff. You can think of the white being like the ferrite and the purple here being like the cementite. And it's interesting that even though on a whole, the whole thing looks like a weird squiggly mess, if you look locally, they're approximately parallel layers, right? So if we look here, we draw a line orthogonal to one leaf, right? We have these approximate parallel equispaced kind of layers of structure, right? Of course, in a micrograph, it's kind of not always easy to determine which phase is which. So this is a hypereutectoid steel. So is white cementite or ferrite in this image? What's that? So white cementite, right? Yeah.
So the boundary is the orientation of the pearlite.
Yeah.
With boundary or?
Their interface. It's cementite ferrite interfacial boundary.
I know. I mean, you can consider like different domains. Yeah. So. Different orientations.
So between different colonies.
Yes.
So with we'll talk about the orientation within a colony later, but yeah, if you have a colony of ferrite that nucleated here and one that grew here, and they impinge together, the ferrite, it's going to be a general high-angle grain boundary between them. But it'll be more complicated than a regular grain boundary because you'll have cementite regions and ferrite regions. Right? So if this is hypereutectoid, so this is allotropomorphic cementite that formed on the prior austenite grain boundaries. In this case, then we would have the pearlite colony would be limited in extent to the size of the austenite grain boundaries, right? Because it's not going to be able to grow past that eutectoid cementite. On the other hand, if this were a hypoeutectoid, right, we would not have the cementite on the grain boundaries, and a pearlite colony could grow to be larger than the original austenite, than the austenite grain size. Right? So if we think about how this pearlite colony can grow, right? So we have a nodule that's growing at a prior austenite grain boundary. So this is austenite grain 1 here, austenite grain here 2. We're growing into this, right? So we have two different orientation relationships that are commonly observed. And again, this is not one that you have to memorize. But if we nucleate on a clean boundary like this, pearlite takes what's known as this pitch-patch orientation relationship, right? So we have there's an orientation relationship between this austenite grain and this new ferrite orientations, right? But there is no orientation relationship with the grain that this is growing into. So it nucleates with an austenite orientation here and then grows into the grain that it doesn't have the orientation relationship with. If we have hypereutectoid cementite at the grain boundary, then we have this Bagriatsky orientation relationship. And there's a relationship between the cementite and the and the ferrite, but there is no relationship between the ferrite and the two grain boundary and the two austenite grain boundaries, right? So basically, it's all down to where nucleation occurred, right? Again, if we nucleated a clean austenite grain boundary, we get this pitch-patch. If we have one that has proeutectoid cementite, right, the cementite in the pearlite is going to have the same orientation as the cementite in the boundary layer, right? And this pitch-patch is very close to Kurgimov-Sachs. Right? Kurgimov-Sachs keeps coming up again and again and again. So all of the ferrite lamella, no matter which case we have, all of these ferrite lamella have approximately the same orientation, crystallographic orientation, right? So it's really like one big ferrite grain with layers of cementite that also have the same orientation, right? And remember, if we're near the eutectoid or we're hypoeutectoid, we have a lot more ferrite than we do cementite. So ferrite will tend to be the percolating phase, right? Ferrite will be completely connected in most ferritic pearlitic steels, where the cementite lamella may not be connected to each other physically. Right? When you're in a hypereutectoid, you have a lot more cementite, and you might have percolating. Both phases be percolating in that case, right? So the question, that should come to mind is, why is the spacing so uniform, right? How does this actually, right? Why is there a sort of a fundamental wavelength, right? Why isn't one lamella much wider or narrower than its neighboring lamella, right? And why is that the case for both ferrite and cementite, right? And we'll talk this through in words before we go through it in the diagram, right? So does the ferrite have a higher or lower carbon concentration than the austenite? Lower, right? So if we're growing ferrite, we have to move, if we're transforming austenite to ferrite, we have to move carbon out, right? Does the cementite have a higher or lower carbon concentration than the austenite? Higher, right? So if we're transforming austenite to cementite, we need to move carbon in, right? So the idea of this is actually pretty simple. Let's say we nucleate a ferrite, right? So we got a small little nodule of ferrite. As it grows, what's it doing? Its carbon is going out, and it's being plowed ahead of the interface. Eventually, it's going to get to a high enough concentration just in front of the interface that you're going to be at a composition at where you're at a high enough concentration to nucleate cementite, right? Cementite's going to suck in carbon, and you're going to have a carbon depleted zone in front of the cementite. Eventually, that depleted zone is going to be low enough that you'll nucleate ferrite. And it just keeps alternating, pushing carbon out, sucking carbon in, right? And the rate at which it happens, right? So if you think about it, that makes sense why the ferrite regions, when you're hypereutectoid, are so much wider than the cementite region, about a factor of 4, right? If you think about the ratio of carbon between those two phases, right, relative to the austenite concentration, it works out kind of, you can make a hand-waving argument as to why that should be, right? Of course, it's not 100% that simple, because we can also branch, right? Both the ferrite and the cementite lamella can branch, and there's some cool work on instabilities that form, diffusional instabilities, that transport instabilities that can form to lead to these things. There is not really a super detailed quantitative. There's many theories, but there is not like a single, like completely coherent theory of pearlite growth, right? But anyway, this is just a schematic of what we talked to. Right, here's the bulk carbon in the austenite. Right, as we grow cementite, we get a depletion zone in front. Once that carbon is depleted enough that it's a little bit below the concentration required to nucleate ferrite, a ferrite lamella will stay, and it will push carbon, pile up carbon in front of it, and eventually it'll get to a region where it's high enough to nucleate a layer of austenite. Okay, so this is a confusing graph. And I apologize, but it's the only one I could find that details what I want to show here. It's really confusing because the temperature axis is backwards. So this is low temperature, this is high temperature, but it's not reciprocal temperature, right? And also, this is reciprocal of the lamella spacing, right? So if this is reciprocal spacing, this is big spacing, and this is small spacings up here, right? So what we want to say is essentially that the higher the transformation temperature, the wider, the bigger the lamella spacing. And at the lower the temperature, the finer the lamella spacing. Okay. Can anyone come up with a coherent argument as to why that's the case? Let's talk this through. Carbon diffusion, right? So at higher temperatures, the carbon can diffuse away faster. So it takes a longer growth time before you build up a layer that's high enough to generate the next layer of cementite. Yeah?
Would it be wrong to think that at the higher temperatures there's less driving force?
That we'll talk about growth of the colony as a whole. Right now we're just talking about the spacing between layers, right? So these are still, we can think about these as being well separated. There's no impingement taking place at all yet, even at the low temperatures where you have a lot of nucleation.
Okay. So it's just like that initial line.
This is just if you're looking within one colony, right, even when they're still fairly small, the layers have sort of this equilibrium spacing. Of course, it's not exact, right? There's a distribution of spacings within any colony, right? But if we think about that sympathetic sideways nucleation mechanism, right, it all depends on how fast that carbon can diffuse, either to fill in the depleted zone, right, or the pushed out ahead in front of the growing interface, right? So it's a pretty simple idea and a very confusing chart, right? And I still confuse myself when I was preparing for class this afternoon. I pulled it up and was like, oh, this is wavelength, right? And I was like, inverse wavelength, so this is like the wave number, but no, it's lamella spacing, right? So I'm sorry, but I haven't not been able to actually find a better chart that just sort of shows these are for different compositions, right? Okay, so we can grow perlite by either adding lamellae, branching lamellae, or the extension growth outwards from the end of the plate, right? So the perlite colony is going to have almost equal rate of growth in all directions, right? Both perpendicular and parallel to the lamellae. It's largely isotropic growth, and we get a spherical in shape, and so therefore when they're sectioned, they will almost always be relatively circular and equiaxed, right? Right. So that's the first sort of indicator that something is actually a sphere, right? If you look at all the cross sections and they're circles, right, compared to if they were, say, elongated, some of them, you would see in cross sections some of the colonies would be ellipsoids, right? Potentially quite elongated ellipses. Right? We'll see the same thing with martensite, right? When they were cut in cross section, they always looked like needles, right? And it was a long time before someone realized if they were actually needle shaped and they were cut in cross section, right? Some of them would appear circular, right, end on. So it's really that they're laths, they're 2D laths, and so that when they're cut in cross section, they almost always look like needles. This 2D to 3D thing is difficult. Okay, so on to the question that you were asking, right? So these pearlite colonies are going to grow unimpeded until they impinge on adjacent colonies, right? So during this time until impingement, the growth rate is going to be relatively constant, right? But after impingement, the pearlite nodules are only going to be able to grow into the remaining austenite between the current colonies, and that's the last stage of pearlite growth, right? And as expected, the rate of this growth is going to be a strong function of temperature, right? So if we start at the eutectoid and we slowly cool down, we're going to increase our growth rate. And then at around 600 C, that's where the maximum growth rate is. And then as we go down, our growth rate decreases again, right? So why does our growth rate decrease again at lower temperatures? All right, it's just diffusion limited, right? Okay. So it's the same balance between driving force and mobility, right? Okay. So the nucleation rate increases with time and temperature. So what do I mean by that, right? So if we have the number of nuclei versus time, right, we sort of have this incubation period where we don't have a whole lot going on, right? Then the nucleation rate accelerates, right? So the nucleation, right? So this is the number of nuclei per volume per second, right? So in the early stages, we don't have a lot. They take off and then plateaus out again, right? So this is due to heterogeneous nucleation at the grain boundaries, right? Pearlite colonies don't nucleate homogeneously, right? So they're not going to follow like Avrami kinetics. They have to nucleate heterogeneously at either the grain boundary, so either at an austenite grain boundary or at a proeutectoid surface, right? So we sort of have an incubation period, then they take off, right? So as the temperature is lowered, the rate of nucleation is going to increase much faster than the rate of growth, right? So if we superpose those curves on top of each other, right? So at where was I? Oh yeah, so as the reaction temperature goes down, rate of nucleation increases faster than the rate of growth, so that means we have a lot more colonies that will form, right? So if we have an isothermal hold at high temperatures or a very, very slow cooling rate, one perlite nodule, it's hard to nucleate, but easier to grow. So we can nucleate essentially one perlite colony, and it will just continue to grow out, and it'll consume a large number, can potentially consume a large number of prior austenite grains, right? So it's not easy to tell what the prior austenite grain size was just by looking at the perlite colony size. Yeah.
Why does the shape of cementite be dendritic and not spherical?
So the shape of the cementite?
As in, why should the perlite be lamellar?
It's this nucleation mechanism, right? Where you're saying why don't you get the instabilities that form that lead to dendrite?
And why is it in the shape as it is now?
Right? It's I'll have to think about that. Why doesn't it form? Right? It has to just, it is just, am I going to say something stupid? Right? I'm going to double check. But basically, if you think you've got a homogeneous field, right, and you're nucleating a little spheroid of either cementite or ferrite, right? And growth is largely isotropic. You're going to be putting carbon out in all directions uniformly, right? Then your next layer is going to form in a sphere around it, right? So at the center of the core, it'd be like layers of, like making a jawbreaker, right? You start with a tiny little piece of candy, and then you dip it, and you just build up layers of, I was going to say shellac on something, right? But there's no driving force to cause an instability like a dendrite on, right? You don't have the heat of formation is significantly lower than the heat of fusion, right? So you don't have like large thermal instabilities, and you don't have any compositional instabilities that would lead to accelerated growth along a specific direction. Right? I'll double check though, right? But I don't offhand see a mechanism why it would, right? But that's not necessarily a satisfactory answer. Not understanding why it would is not the same as saying exactly why it doesn't. All right. Okay. So back to this. If we are at a high temperature or have a very slow cooling rate, one perlite nodule can grow large enough and consume multiple austenite grains. Right. If we're at a lower temperature or a faster cooling rate, we nucleate a large number of perlite colonies at the austenite grain boundaries, right? And then they will grow in and they will impinge fairly quickly, right? And now we'll have a large number of perlite colonies growing into a single austenite grain, right? So in each of these conditions, right, we can't think of this in terms of random nucleation, right? It's always grain boundary nucleation. And so mathematically, the treatment of this is pretty difficult, right? JMAC Avrami doesn't sort of work, and the temperature, the transformation rate is going to depend on the initial austenite grain size, the austenite grain shape, and the transformation rate is going to decrease with increasing austenite grain size. Right? If we're in a nucleation or a growth limited regime where nucleation is easy, right? Our rate is going to be proportional to the amount of nucleation sites that we have. Okay. So, some basic properties. So here we have yield stress versus undercooling. Right? So as our undercooling goes up, our yield stress increases. Right? So how do we make physical sense of that? As our undercooling increases, what happens to our lamellar spacing? It decreases. So the mean free path for dislocations is shortened. It's essentially a slightly more complicated Hall-Petch effect. Right? It decreases the amount of space that dislocations have to move. Right? Of course, it's a little more complicated than that because here we've got these spherical sort of layers. So in some regime, you're traveling parallel. Your dislocations are going to have easy transit between the plates, and in other regions are going to be running, right? So the slope of this tends to be slightly less than a Hall-Petch type slope. Okay. Right. Work hardening of the alloy tends to increase with pearlite, right? So what this tells us is that in a ferrite pearlite steel, the pearlite work hardens faster than the ferrite. Right? Does that make sense? Right? We're in a confined space, right? You have less room for dislocations to get out of the way, right? They get tangled up more easily. They pile up more easily. Right? Right? And of course, as you could probably guess, pearlite is going to have a dramatic effect on toughness, fairly negative effect, right? It's easy to nucleate cracks at the ferrite cementite interfaces. All right. New cracks can nucleate at the interface. Then we have a high degree of work hardening, limit the plastic deformation near cracks, and we're going to have a much lower energy absorption. Right. So this is like Sharpie impact temperature as a function of temperature for various amounts of carbon. Right. So here's the ductile to brittle transition, but depending on the amount of pearlite you have, you're going to lower the energy absorption, the amount of energy that's absorbed for fracture. Right? And then I was going to go into ferrite pearlite steels because this is really a high proportion of steels used in industry, but we'll get started with this Friday.